Hello, I wanted to make a quick calorimetry video to not only give you an example of a calorimetry problem and how to solve it, but more importantly, calorimetry, understand it as a lab experiment and what we need to do in case it's a free response question. All right. So, because calorimetry is a lab, it's fair to expect to see this in a free response section. And because of that, I wanted to kind of key you in on some of the things you need to be aware of and make sure that you write down as you do your free response answer. First thing, understand that calorimetry is based upon the law of conservation of energy, that the heat is never created or destroyed. It's merely transformed or transferred from one to another. And we're going to utilize that in calorimetry by having the heat lost or gained by an experiment equal absorbed or taken from a solution around that experiment, in which case usually it's water. But they may use the general term solution, which is actually what's used in the example I'll do. And then, so basically, you can calculate the heat gained or lost by water simply by measuring its temperature change. All right, so here's the setup for calorimetry. First thing you need to do is you need to have it the reaction take place in a container, and it's defined, it's measurable, meaning that you can make measurements in this container, and we need also, as you'll see, it to be isolated. All right, so as we do our free response, we're going to say it's going to be in a container. You fill it up with water or a solution. Now you need to know exactly how much that is. So it will be with a specific amount of solution. And you can have your reactants, which will then be put in. And now the key point is that the water is post-displacement, meaning you can't put 100 milliliters in there and then add reactants and say you have 100 milliliters of solution because of displacement. The physical presence of those reactants will increase the volume from 100 milliliters to some other little bit higher, maybe a lot higher, who knows, depends on how much you have. And so it's always post reactant that is your solution amount. All right, so what we need to do is we need to be able to accurately measure the change in temperature. So we need a thermometer. But if the thermometer is touching the bottom, you have introduced potential error. You've introduced uncertainty into your temperature measurement. To what extent is that temperature that you are reading accurately reflecting the temperature of the water or solution, as opposed to it being affected in some way by the material of the container wall or floor? Same thing happens if it's on the walls. So we do not want the container to in any way affect our temperature. So we are going to state the thermometer is suspended in the middle of a container. By suspending it in the middle, suspending means it's not touching the bottom. In the middle means it's not touching any of the sides. So now we've eliminated that source of error. And believe me, readers will be looking for that. All right, so calorimetry club. What happens in the reaction stays in the reaction. With this setup right now, we're losing heat. We've all seen steam escaping containers. Well, we don't want that because that is a source of error. We need to contain this. We need to have the water absorb all the heat or from this reaction, or nothing extra from external to this system needs to be able to enter it. So we're going to prevent that error by putting a lid on it. So in a covered container is now our new adjective to describe our container. However, by the same logic, we can't have any heat escaping through the container, through the sides of it. We've all held paper cups that are almost too hot to hold. That's because heat is just leaving through the sides of the container. The liquid's still inside it, but the heat is escaping. However, we've held thermos, which has super hot coffee in it, but you can't feel it because it's insulated. So we're going to eliminate this error by saying it's in a covered, insulated container. So now we have properly set up our calorimetry experiments, and we're ready to kind of begin. Now, what we're going to do is we're going to begin with the end in mind. We want to be able to calculate the heat of the reaction using this Q is equal to MC delta T formula, delta T being changing temperature. See, I think is capitalized. Sometimes it is, and I need to look into that. Sorry. Either way, don't freak out if it's different than what you see. M is the mass of the solution, and that's beforehand. We'll get to that later. C is what's known as specific heat, and this is essentially how quickly a substance, a material, is able to absorb and release heat. Now, many of us, if you've cooked, you know about this phenomenon, that if you put a lasagna in the oven in either a metal or glass pan, and then at the end you put aluminum foil on it, and then you take it out when it's done cooking, let's say 45 minutes later. 5 minutes later, if you tried to touch that metal or glass pan, you'd burn your hands. But you can just reach and take that aluminum foil off without any issues, because the aluminum foil, aluminum specific heat is such that it gains heat quickly, but it also loses heat and it cools off really quickly. So in no time at all, you're able to remove it without fear of burning yourself. And that's what the whole concept of specific heat is all about. All right. So we're going to use now, you can use the fact that the specific heat of water is known, as well as if it's a set specific amount, you know how much the mass is, and then we're going to measure the delta T for that water. So we have two different Q equals MC delta T's, but we can kind of not have to use both full formulas, given the fact that we have set up our calorimetry. It's kind of a coffee cup calorimetry is what people say. It's that insulated covered container lets us then assume that the Q that you get for water is equal to the negative Q for the reaction. And this is that law of conservation of energy being applied. We have isolated the reaction and the water from the outside world, and therefore any change in the water's temperature has to be due to the reaction. So if the temperature goes up, it means it's absorbed heat, which means the reaction has to have given off heat. In other words, negative of one is the positive of the other. So a negative Q reaction is exothermic, meaning heat energy is lost. Okay. So basically, now we're going to run the experiment. We're going to, in my experience, what we usually are doing in these things, problems, is you're solving for C, like there's an unknown metal, and you're going to use all the calorimetry data that you gather to determine what that metal is, given your calculated C value, and you compare that with the table of known C values for metals. Or you'll be solving for Q of a reaction, how much energy is given off when this reaction is run. Okay, so data, what data do we need to record as we do this experiment? We just, Q, M, C, delta T, just record that data. Now, be careful, because this is a free response trick. You can't measure delta T. Delta T is a calculated value. You can measure starting temperature and ending temperature from which you calculate delta T. But please, in any free response question, don't write down and then we measure delta T, because they'll mark that wrong. You're going to measure starting and ending temperature from which you calculate it. So that's something to be aware of. All right. So here we have an example. Determine the enthalpy change for the reaction where 2.2 grams of magnesium is added to enough HCl to make a 100 milliliter solution. The reaction takes place in a coffee cup calorimeter, and the temperature starts at 26.3 degrees and ends at 58.3 degrees. Then you're given a balanced equation and two other facts. Now, in this case, it's given to you. Sometimes you may have to look it up from a table, but they're going to say to you that, hey, this density of this solution is 1 gram per mole, and the specific heat of this solution is 4.18 joules per gram per degree Celsius. Now, get used to those numbers because the density of 1 gram per mole is that of water, and the specific heat of 4.18 joules per gram per Celsius is that of water. Those are used very, very, very commonly. In this case, we're calling it a solution because it's hydrochloric acid, which is a mixture of the acid and water. But I guess for simplification's sake, it's just been given to us to run with water's numbers here. Fair enough. We'll run with it and go. So first thing I do is I always write down the formula to solve for the problem. They're asking us what the enthalpy change is. Now, I write down delta H for the reaction, change in enthalpy for the reaction. Well, we know that's just equal to the heat of the reaction, Q reaction over the moles of magnesium. Well, here we have a situation, though, where delta H we don't know, but we also don't know what Q reaction is or moles of magnesium is. The general rule of thumb to always keep in the back of your head is that for every unknown, you can only have for every equation, you can only have one unknown. So if you have one unknown and one equation, you can solve it. But if you have one equation and two unknowns or three unknowns, you can't solve it. So this is unsolvable. We can't solve delta H right now. What we need to do is get rid of some of those unknowns until there's only the one unknown we're solving for. And the good news is we can solve for Q reaction using the Q is equal to MC delta T plus all the data we've been given. And we can solve for moles of magnesium simply by using, grams divided by its molecular mass is moles. So just with those calculations, we'll be fine. And then we'll be able to take those numbers and solve for the delta H reaction. That's our plan of attack. All right, so here we have the same problem, and the M there is a sign of my psychic abilities. Q of the solution is M solution, C solution, delta T. And first thing we should then see is that we only know one of those four things. And again, we have the same situation where we have one equation and three unknowns. We only want one equation, one unknown. Well, we'll need to start figuring out what make those unknowns known. Delta T is easy. We'll get to that in a minute. Let's look at M solution. So M, and this is key point here. Look at how awkwardly the phrasing is on this problem. It says determine the enthalpy change of a reaction where 2.2 grams of magnesium is added to enough HCl to make a 100 milliliter solution. It seems weirdly phrased, but that's actually very precisely phrased. Basically, it's saying that after displacement, you've got a 100 milliliter solution. So that's what it's getting to. So now you can just run with that 100. So now we know we've got a 100 milliliter solution. Now this is before the reaction. So that's our starting numbers. So we can run with it. Keep that in mind. In other words, the fact that you added 2.2 grams or 5,000 grams doesn't matter yet. They haven't reacted yet. That number doesn't come into play. All that matters is how much solution you have. And since we know the density, we can then calculate the grams. 100 milliliters, and the density is 1 gram per milliliter. 100 milliliters, 100 grams. That's the nice thing about water, is that if you're in calorimetry, if you're dealing with water and it's a 73 milliliter solution, well, it's 73 grams of water, which is nice. Okay, so then we do easy calculation for delta T. It's 58.3 minus 26.3, 32.0 degrees Celsius. So now we've got two more knowns. We can now solve for Q solution by plugging those in. And look at me nicely crossing out, tracking and crossing out units. This is a skill you need to do. It will save your life or help you pass, either of which is a good result. So this prevents dumb mistakes. So make sure you do it. And as you can see, we're starting to see some pretty weird units. Joules per gram per degree Celsius, right? Things that aren't going to be common sense. So you can't rely anymore on just knowing. Write it out, cancel it. This is what your time is wisely used for in the free response time. So do the math, you get 133 joules. Now, get rid of all that. And again, write down the formulas. Well, we know that, first of all, that the heat absorbed by the solution had to be lost by the reaction. So Q reaction is going to be the negative of that. So it's negative 133 joules. All right. So I'm going to write down the formula again. And I see how I wrote it fresh. I'm not doing anything in my head. This again prevents dumb mistakes. So I've written it fresh. I now know, whoops, I have to figure out moles, so I don't know why it's printing out that way, but basically here's the math to figure out that you have 0.09 moles. And so now we can plug our two things that we now know into this formula. And we've got negative 133 joules over 0.09 moles is negative 1478 joules per mole. And we're not done. Don't be done yet. Take a look. We started off with 2.2 grams. Now, retroactively, this is kind of tricky, and I want you to pay attention to it. It didn't matter in this case, but there are two rules for sig figs. And this is the sig fig answer, by the way, is going to be negative 1500. But we did addition and subtraction when it was the 58.3 minus 26.3. But the thing is that's a decimal point. So we do have 3 sig figs after the addition and subtraction. So our limiting sig fig is in fact the 2.2 grams we started with, which is 2 sig figs. So our answer is limited to 2 sig figs. So the final answer is negative 1500 joules per mole. Now, I have no clue. I grabbed these numbers and randomly threw numbers down, so I don't know if that's anything near reality for magnesium. So don't ever quote that. But in terms of the math and the process, it's good process. So good luck. But yeah, the key part as you write this down is recognize that words matter, and you need to be very particular to account for all sources of error and isolating them and eliminating them as you set up your experiment. Thanks. Bye.